Okay, in the last video we ended with introducing the idea of decomposing a vector into a sum of two orthogonal vectors. So here's where we want to kind of develop some formulas and a method for doing that. So let's suppose that the vector that we want to decompose is called u. And then let's suppose we have some other vector a that we would like to project u onto. So here's kind of an image of that. Here's our vector u, and here's our vector a. Notice these are not necessarily orthogonal, and they don't have to be. Just like how v naught up here is not necessarily orthogonal to either of these. So just any two vectors, u and a. And what we want to do is project u onto a. And what does that actually mean? Well, if you imagine there being some kind of light source directly above this image, kind of shining, perpendicularly down to A, it would cast this shadow on vector A. And I could think of the vector that has the same initial point as u and goes the length of that shadow as the projection of u onto A. We're going to call that projection W1. So you can see here in this next image, the projection has been created and named W1. Then what we want to do once we have W1 is find a vector, and it turns out there's only one vector that will work for this, but a vector that we're going to call W2, such that W1 plus the second vector W2 gives us our vector u that we started with. That would be decomposing u into a sum of two orthogonal vectors. Okay, so W2 has to be orthogonal to W1, and we always find W1 first and then use that to find W2. These next two images here just kind of show you some other cases. In this case, W1 ended up being in the same direction as A but shorter. If U is a much longer vector, then projecting U onto A may require you to extend a little bit to get the entire shadow. Nothing changes in the calculations for this. It's just what the visual looks like. If the vector u forms in an angle that's greater than 90 degrees, so an obtuse angle with vector a, then the projection of u is going to cast a shadow behind a, and in that case we just put a line through a and use that line for the projection. But again, that's all for the sake of the visual. None of that affects the calculation that we do. So here is the expression that we're looking for. U is going to end up being a sum of W1 and W2, which are going to be orthogonal vectors. So given a vector u, how do we come up with this W1 and this W2? Well, we're going to use a theorem which is going to state the existence and uniqueness of those vectors W1 and W2. And in the process of proving this theorem, we'll automatically come up with a formula for determining them. This proof is straight out of your book, so we're just going to discuss it here to make sure you understand the steps. So as we saw on the previous page, we're going to assume u and a are vectors, but this time we're going to assume that they're in Rn. There's no need for them to be vectors that we can easily visualize, meaning vectors in 2 space or 3 space. This will work for any vectors in Rn. And we're also going to assume that A is a non-zero vector, because you can't project a vector onto the zero vector. Then this theorem is going to state that under these assumptions, u can be expressed in exactly one way in the form W1 plus W2, where W1 is a scalar multiple of A and W2 is orthogonal. Notice back on this previous page, we were calling W1 the projection of U onto A, but the projection always creates a vector that is either that's parallel to A. It either points in the same direction or the opposite. So that would mean that this W1 can alternatively be thought of as a scalar multiple of A. And that's the way the theorem is stating this. So coming back over here, let's talk through this proof. Okay, so the statement here says that W1 should be a scalar multiple of A. So in other words, we want to show that we can find some scalar k, which when multiplied to A gives us the vector W1 that we're referring to in that proof. Okay, so our primary goal here is to determine what that scalar should be if we're given u and a. And then we also want to use this to come up with a vector W2 such that the sum of these two vectors is equal to u, and these two vectors are also orthogonal to each other. So we actually start with this expression, and we make this substitution for W1. U should end up equaling W1 plus W2, but W1 should be Ka, some scalar times A, and then plus W2. Okay? So now what we're going to do is we're going to take a dot product of U with A and rewrite U in this form up here. And then we want to apply some properties that we already know about of the dot product to write this in a specific form. So let's take a look at this here. If I rewrite U as Ka plus W2 like we did up here, and take the dot product of this vector with A, we know that the dot product has a few useful properties. It can distribute over this sum, for one thing, and a scalar times a vector dotted with another vector, I can use the homogeneity property to dot the two vectors first and then multiply the result by a scalar. In addition to that, when I distribute the A to this first term, I'm going to have A dot A there, which we know is the same thing as the norm of A squared. So doing the distributive property and using those additional properties of the dot product, we get this expression. U dotted with A is equal to K norm of A squared plus W2 dotted with A. However, remember, we want this vector W2 to be orthogonal to W1, but W1 is a scalar multiple of A. So that would mean that W2 is also orthogonal to A, which by definition of orthogonality means that this dot product should equal 0. So this equation reduces down to just U dotted with A equals our scalar K times the norm of A squared. That's something that I can solve for K. K is equal to U dot A over the norm of A squared. This is kind of what we were looking for, because everything on the right side of that equal sign there would be known at the beginning of the problem. U and A are vectors that we are given, and the goal is to find the vectors W1 and W2. So you have everything you need to compute this. Now, where did K come from? K was the scalar multiple, or the scalar that we multiplied A by to create W1. So that means W1, let's see if they wrote that in here. They write it down here. I'll write it separately here. W1 should equal this scalar, U dot A, over the norm of A squared times the vector A. So that's a scalar times a vector right there. And this is a formula for coming up with that projection of U onto the vector A. Now, how do we use that to come up with W2? Well, it's pretty easy now, because if we are looking for W2, remember that's the unique vector that can be added to W1, which gives me U. But if I just solve this for W2, I see that W2 should be equal to U minus W1. And so that's where we get this definition right here. W2 is equal to U minus W1, but W1 we have an expression for, so we can write that as U minus U dot A over A, norm of A squared times A. Okay? Now, we would have to then prove that this is orthogonal, which you can do by taking the dot product of W1 with this expression right here. That's a really good exercise for you to do. You want to show that that dot product is equal to 0 to show that they're orthogonal to each other, and it would require you to use some of those properties of dot products. I like that example because there's some things in here that are scalars but kind of look vector-ish because they involve vectors in their formula. So keeping track of which things are vectors, which things are scalars, which properties of dot products you need to use, it's a really good exercise. So try doing that. Take the dot product of this expression with this expression, show that it's equal to 0. But that would wrap this proof up, because that gives us the orthogonality condition. Okay, so those two vectors that we just found, W1 and W2, the theorem is simply stating that they exist and they are unique. we give names to those. We don't always call them W1 and W2. In fact, W1, which was, remember, the shadow of U onto the vector A, the projection of U onto A, we call that the vector component of U along A. I've been calling it a projection, but this is another term. This is what your book uses to describe that. The other vector, W2, which we found was equal to U minus W1, we're not going to give that a special name. We just call it U minus this vector component of U along A using this notation. And we called this vector, the result of this, the vector component of U orthogonal to A. So the difference is along A and orthogonal to A. Okay? So let's use this in an example. I have a vector U and a vector A, and we want to find both of those vector components, the vector component of U along A and orthogonal to A. And then we want to show that these two vectors are orthogonal just by using the dot product. So let's start with the first one. I want to find the projection of U along A. And notice the vector that we're projecting onto is the one that shows up as a subscript here. Okay, so the formula that we just came up with said that we need to do U dot A up here, 2, 1, 4, dot negative 1, 0, 5, over the norm of A squared. Now, remember, when you normally take the norm of a vector, you're adding the sum of the squares of its components, and then you're taking a square root. So the norm of A squared is simply going to eliminate that radical, which means I can think of the denominator of this thing as just the sum of the squares of the components of A. That's negative 1 squared plus 0 squared plus 5 squared, which would be 26. Okay? A lot of the time you can do those mentally after some practice. That's the scalar that we multiply the vector A by to give me the projection of U onto A, or this vector component of U along A. So I have to multiply that to the vector negative 1, 0, 5. Okay? Now this, if you evaluate this dot product, is equal to 18 over 26. And we're going to multiply that to our vector here, negative 1, 0, 5. I can simplify that to 9/13 and then multiply the scalar in, giving me negative 9/13, 0, 45/13. So we're halfway there. We have our projection of U along A. Now we need the projection of U orthogonal to A, the vector component of U orthogonal to A. So that's this guy, U minus the projection or the component that we just found. Okay, well, U is 2, 1, 4 minus the vector we just found, negative 9/13, 0, 45/13. Okay, so doing the subtraction here, you're going to get the vector 35/13, 1, 7/13. Okay? And that gets us both of those vector components that we were looking for. The last thing we were asked to do was show that these are in fact orthogonal to each other, because they need to be orthogonal to each other to do what they're supposed to do. That's just a matter of taking the dot product of these two vectors, negative 9/13, 0, 45/13, and then 35/13, 1, 7/13. I'll leave it to you to show that the dot product is equal to 0. You can do those calculations on your own to verify, but we do end up getting 0 in this case. Okay? Now, sometimes when we're doing this process, we don't necessarily always want the entire decomposition of a vector into the sum of those two components. In fact, sometimes all we care about is the projection of u along A, or the vector component of u along A. And in many cases, it's not even the entire vector that we care about. It's just the magnitude of that vector. So the quantity that we get by taking the norm of the vector component of u along A is sometimes called the scalar component of u along A. Scalar because it's not a vector, it's a scalar. Okay. Now, with that idea, another thing that we're oftentimes doing, when I do this kind of projection here, go back to this page, when I do this kind of projection in an application, projecting u onto this vector A, usually the vector A is one that we select for a specific purpose, and usually that purpose is to give us a particular direction. Oftentimes this vector A is a normal vector to some kind of a surface or a curve. In Calculus 3 we deal with that a lot. And for simplicity, because we're selecting this vector and the direction is usually the only thing that actually matters, since our projection is going to scale that thing anyways, for simplicity we usually choose this vector to be a unit vector. So in a lot of applications where we're doing this, we're thinking of A as a unit vector. And when we do that, our projection formula becomes much more simplified. You should verify this. If A is a unit vector, then the norm of A will be 1, and our projection formula reduces to just this, right? But if A is a unit vector, then the norm of this vector is exactly equal to this scalar right here. So that would say that in the case of A being a unit vector, the scalar component of u along A represents, or is given by the dot product of u with A. In most applications, this is the way we're actually thinking about the dot product. We interpret the dot product as a projection or a scalar component of a particular vector along some unit vector. So if we go back to this example back here, notice I decomposed this initial velocity vector into a horizontal and a vertical vector in 2 space. I can think of this as a scalar multiple of I, and this as a scalar multiple of j, my standard basis vectors. If all I care about is the magnitude of each of these vectors, that would be the scalar that I'm multiplying I by to get v naught x, and the other scalar I'm multiplying j by to get v naught y. That would represent the speed in each of these directions of this projectile. And I can get those speeds directly by just taking the dot product of my initial velocity with I and my initial velocity with j. So v naught dotted with I gives me the horizontal speed. V naught dotted with j gives me the vertical speed. That's one way of looking at that. Okay? All right, one last thing to wrap up this section. We can now generalize the Pythagorean theorem. Notice if we're talking about vectors into space. If I have 2 vectors, u and v, which are orthogonal to each other, and I add them tip to tail, so u is here, v tip to tail, it's going to go here, then the sum of u with v forms the hypotenuse of a right triangle. So I could say that again, if this is in 2 space, the length of this side squared plus the length of this side squared would equal this side squared. But in terms of norms, which are the lengths of those vectors, that can be represented by this. The norm of u plus v squared equals the norm of u squared plus the norm of v squared, as long as u and v are orthogonal to each other, because that's what's giving us a right triangle. It turns out that this is not only true in R2, it's true in all of Rn. In other words, if you have any pair of vectors in Rn that are orthogonal to each other, this equation will always be true. Now to see why, it's a very straightforward proof. Let's let u and v be vectors in Rn, and let's also assume that they are orthogonal to each other. That means their dot product is equal to 0. Well, if I evaluate the left-hand side of this equation, the norm of u plus v squared is just the dot product of u plus v with itself. Now, if we use those properties of dot products, namely the distributive property and the symmetry property, I get this, u dot u plus u dot v plus v dot u plus v dot v. These two terms on the outsides are the square of the norms of u and v respectively. And then because of the symmetry, u dot v is showing up twice here, so I can call that plus 2 times u dot v. However, the assumption that u and v are orthogonal would make this entire term equal to 0, giving me just the sum of the squares of the norms of u and v. That's what the equation was saying in the first place. Okay, so let's use this on two vectors in R4. I want to show that the Pythagorean theorem holds for these two vectors. Now, in order to do that, remember, the Pythagorean theorem will only apply if these two vectors are orthogonal in the first place. So we need to verify that these two vectors are, in fact, orthogonal. 1, 0, 4, 5, dotted with -5, 6, 0, 1. This does in fact equal 0. You can verify that by doing a dot product yourself. Next up, we need the norms of three different vectors. I need the norms of each of these as well as the norm of their sum. And I'm going to confirm the Pythagorean theorem with that. So what is the norm of 1, 0, 4, 5? Well, in fact, we don't even need the norm specifically, because in the Pythagorean theorem, we're always squaring those norms, which, remember, just gets rid of the radical when evaluating a norm. So really, the norm of this thing squared should just be the sum of the squares of these components. 1 plus 16 plus 5, that would come out, 1 plus 16 plus 25, that would be 42. If I do the same thing with my second vector there, -5, 6, 0, 1, find its norm and square it. That's going to be 25 plus 36 plus 0 plus 1. That should be 62. Okay. Now the next thing I want to do is find the norm of the sum of these two guys, or the norm squared. So let's start by adding them. 1, 0, 4, 5 plus -5, 6, 0, 1. What is that? That should be -4, 6, 4, 6. What is the norm squared of that vector? That's -4, 6, 4, 6. I'm adding the sum of the squares, 16 plus 36 plus 16 plus 36. That's 104. Now to verify, if the Pythagorean theorem is true, the fact that these two vectors are orthogonal would imply that the sum of these two numbers should equal this. But that's true. 42 plus 62 is equal to 104. And so that verifies that the Pythagorean theorem worked for these two vectors in R4. Okay, that's it for 3.3.